Electron configurations. So an electron configuration is going to be a simple way of showing a energy level diagram and a much more condensed version of it. So you can imagine if we had an energy level diagram, we could put one electron in the 1s, we can put two, then it's full, put another one in the 2s, two of them makes it full. So if we had 5 electrons, we'd put our last one in the 2p orbital. So in this one we have a 1s orbital with 2 electrons in it, a 2s orbital with 2 electrons in it, and a 2p subshell, which has 3 orbitals, one of them having 1 electrons. An electron configuration would take that information and write it out in a condensed way. So this 1s electron is written there, and we use the superscript to denote how many electrons are in that 1s orbital. The 2s orbital comes next in our writing, and because it has 2 electrons in it, we have a superscript of 2 written there. The 2p subshell, we're not going to differentiate between the orbitals. We know that there's 3 of them. Each one can hold 2 electrons. So there'd be up to 6 electrons that we could put in the 2p. So if we wanted to do the electron configuration for, let's say, neon, we would have more electrons in the energy level diagram. Let me draw them in the diagram. And its electron configuration would say that our 1s orbital has 2 electrons in it. Our 2s orbital has 2 electrons in it. And our 2p orbital has 6 electrons in it. So based on the electron configuration, you can get an idea of what the energy level diagram would look like. It's just not showing the staggering or the actual drawing of the electrons. Then we can make it even more concise by writing what's called a shorthand electron configuration. And essentially what this does is it uses the noble gases to skip ahead without having to write each one of them. So for example, if you look at the electron configuration for sodium, its valence electron, the last electron, is a 3s electron. So we would write 3s with a superscript of 1 above it. But it is only 1 electron more than what neon has. So instead of writing out all of the work for neon, because remember, this is what neon's electron configuration would look like, just that part in the square brackets. It is what neon is, plus an extra 1 electron in the 3s orbital. So the shorthand electron configuration says, all right, I'll take what neon has, without having to write all of that over again, and add in a electron in the 3s orbital. That's a shorthand electron configuration. There are these electron configurations that you're going to see that are not what you'd expect them to be. So we use the word anomalous electron configurations. And the reason for this is because sometimes if the electrons can put themselves in a slightly different way that is going to be more stable, they will do that. So they might not be where you expect them to be because they've moved into a particular situation which leaves them being more stable. And we see this a lot with a half-filled d orbital. So it turns out that a half full or a full d orbital is relatively stable when it comes to electron arrangement. So for certain elements, what they'll do is they'll move their electrons around. They won't gain or lose them. We're not talking ions here. They will just move their electrons into an anomalous electron configuration. So let's see what that looks like. So copper, you'd expect to be, if you have a periodic table in front of you, you take what argon has, and it's beyond argon. So you take what argon has in terms of electrons. We're doing a shorthand electron configuration here. Add 2 more electrons into the 4s, and then we start into our D. And copper's the 9 electrons away, so it's almost right at the end there. So you add 9 electrons into the 3d subshell, and that is what you'd imagine copper's electron configuration to be. The thing is, a d orbital, when it has 10 electrons in it, is much more stable than a d orbital with 9 electrons in it. So if it could gain that 1 electron, it would be stable, but that would be an ion. And we're not talking about anomalous electron configuration for ions yet. We're talking about atoms here. So instead of gaining an electron from somewhere else, it actually shuffles its own electrons. It takes one of the 4s electrons and it puts it into the d. So that's how we can get a full d subshell. But it does come at the cost of the 4s is now down to 1, and the 3d subshell is up to 10. So the actual electron configuration for copper, and we can see this as written on the periodic table, has moved one of the electrons out of the 4s and put it into the 3d, because having a full d subshell happens to be a stable configuration. And this can happen with a half-filled d subshell as well. So anomalous means not exactly what you'd predict, and this is what you'd predict just by following along, adding electrons along the periodic table, but because we have a chance of having a full d subshell, if we just borrow one of these electrons over from the s, and that turns out to be more stable, then that is what happens for copper. So anomalous electron configurations, again, remember they're not ions. We're not talking about them losing electrons or gaining electrons. They're moving their own electrons. So they're moving from one subshell to another so that they become more stable. Silver is another one. So if you look at silver, if you were to look up its shorthand electron configuration, you'd see that it's taken one of the electrons from the 5s and it's used it to fill out the 4d, because atoms find having a most silver atoms anyways, find having a full d subshell is more stable than having two in the 5s. So it borrows that one from the 5s, puts it into the 4d so they can have a full 4d. So the silver ion does a similar thing. Here it is here. It has lost, this is a positive 1 ion. So if you had, let's go over here, this is your silver atom, and it is going to have an anomalous electron configuration, but it still has all of its own electrons. It just moves one into the 5s and puts it into the 4d. Now let's think about a silver ion. So if a silver ion has a positive 1 charge, it has lost 1 electron. So if you look at this and you say, okay, which electron should I lose to leave the most stable configuration? And we just said having a full 4d is stable, so we don't want to mess with that. So when silver does have to lose its electron, it loses the 5s. So imagine it had the 5s, it lost that 5s 1 electron, and that is how it now became this positive 1 charged silver ion.